Good afternoon. I'm Lisa Grissom with the Science History Institute. I'm delighted to welcome you to the annual Chao Symposium on Innovation, where we explore, celebrate, and encourage innovation and sustainability in the chemical sciences. For our program today, we will have opening remarks by Albert Chao, President and CEO of Westlake Chemical, and David Cole, President and CEO of the Science History Institute, who will introduce 4 presentations by innovators in the theory and practice of sustainable chemistry. There will be a Q&A at the end of the program, so please put any questions or comments in the chat as we go. Now, to begin our program, I am pleased to introduce Albert Chao. Albert.
Thank you, Lisa. Good afternoon, ladies and gentlemen. I'm Albert Chao, President and Chief Executive Officer of Westlake Chemical. Westlake was founded in 1986 by my father, T.T. Chao, a pioneer in the global petrochemical industry, starting in Asia in the 1950s. Today, Westlake has grown into an international manufacturer and a supplier of petrochemicals, polymers, and building products that enhance the daily lives of people around the world. Whether it's plastic wrap that keeps our meats and produce fresh, the intravenous bags and tubing used in medical care, the pipes that are essential to delivering clean water, or the chlorine that treats water and helps keep our pools safe. Westlake plays a vital role in supplying the building blocks for these products and many more. As a leading global producer of various polymers, we understand the importance of reducing the environmental impacts of our feedstocks, production, and usage, and are developing exciting innovations together with our customers to meet their objectives while also reducing environmental impacts. In the future, we are prioritizing implementation of additional environmentally friendly innovations like our low-carbon green bean caustic soda and PVC products by incorporating recycled and bio-derived materials, while, of course, maintaining product quality. Sustainability and green chemistry are of vital importance to Westlake and the industry as a whole. For many years, Westlake has been examining our activities and our work against the growing body of global sustainability benchmarks. Our intention is to use these insights to help us better allocate resources, make more impactful decisions, and take action to advance continuous improvement in sustainability. These reports and the directives may be found at westlake.com/ESG. Our continued focus on environmental, sustainability, and governance activities have led us to make significant improvements in our operational and supply chain processes for the betterment of communities where our people live and work, and where our products serve vital and valued purposes. For example, we are investing in continuous improvement projects at the manufacturing locations to reduce energy, waste, water, and carbon footprints. Among the ways we support innovations in sustainable chemistry is through this annual symposium named in honor of our father. My brother James and I agreed that the T.T. Chao Symposium should have a long-term focus on environmental sustainability and innovations that are green and those that can combat global warming and other sustainability challenges. This year's focus on innovations in green chemistry shall present 4 leading academics and innovators, entrepreneurs who are focused on areas such as mechanical chemistry, as chemistry without harmful solvents, sustainable management of plastic waste, sustainable separation of metals, and new methods for treating water. are proud to partner with the premier storytellers of the history of science to share with you all the innovations unfolding that will surely inform the development of green chemistry. It is my pleasure to now introduce you to David Koh, the president of Science History Institute.
Albert, thank you very much, and a warm welcome to all of you joining us today. On behalf of the Science History Institute, I wish to thank the Ting, Tsung, and Fong Chao Foundation for their generous support of the annual Chao Symposium. Today and in the future, the Chao Symposium will focus on sharing stories of creative thinking and new technologies in green chemistry, chemical innovations that address the pressing environmental sustainability challenges of our time. Our program today will present 4 sterling examples of sustainable chemical innovation shared by leaders in chemistry and in allied fields. The insights our presenters will share with us promise to resonate globally. Indeed, this program will be shared very soon with a large global audience of researchers, entrepreneurs, and students of all ages via YouTube and through the Science History Institute's content sharing partnerships with schools and nonprofits in countries around the world. Following our 4 featured talks today, I invite you to participate in a question and answer period with the presenters. Please feel free to post your questions during the talks via the Zoom chat feature, and please enjoy the presentations. And now, it's my pleasure to introduce our first speaker, Dr. Eric Shelter. Dr. Shelter is director of the National Science Foundation Center for Sustainable Separation of Metals and professor of chemistry at the University of Pennsylvania. For the past 12 years, Dr. Shelter has developed an internationally recognized research program in synthetic, inorganic chemistry, and separations chemistry. Much of his work focuses on discovery of chemical methods to separate critical metals from natural and anthropogenic sources that are efficient and reduce waste. His work and leadership on sustainable metals separations have been recognized by the Department of Energy, the American Chemical Society, and the Environmental Protection Agency. He also has more than 10 years of experience in public outreach efforts related to the chemical, social, and political aspects of critical materials. His presentation today is entitled Sustainable Separations to Meet Emerging Needs in Critical Metals. Dr. Shelter, welcome.
Thank you, David. Okay, can you see my slides, David?
Yes, sir.
All right, great. Well, thank you so much. And thank you for that kind introduction. I'm just so thrilled to be a part of the Chao Symposium on Innovation this year. And I'm really grateful for the opportunity to tell you about some of the chemistry that we've been developing, both in my group and as part of a wider effort in what's called the Center for Sustainable Separations of Metals. So this is an NSF, National Science Foundation supported center, which is examining this larger problem of critical metal separations that I'll talk to you a little bit about today. So I thought I'd start out the discussion with somewhat of a positive message. We have recently concluded the COP26 Climate Change Negotiation Conference. And in those recent versions of the conferences, the news has been somewhat depressing around meeting global targets for things like emissions of climate altering gases. And so I wanted to start out with a piece of positive news in this area related to the field of climate change. And that is this report that appeared this fall from the Institute for New Economic Thinking at the Oxford Martin School that talked about how the price of renewable energy really has undergone a tremendous transformation in recent years, and one that was really unprecedented and unexpected. So what these economists showed is that the price of, for example, solar photovoltaic per megawatt has really gone down at a surprising rate, and one that economists really had not anticipated. And so it is my opinion that science and technology are really winning when it comes to developing the alternative renewable energy technologies that we will need for the support of grid scale power going forward in the coming years. Moreover, there have been some pretty exciting policy developments in the US in the past couple of years related to transportation, which is another big issue around sustainability and trying to limit emissions to ultimately mitigate the impact of global climate change. So we had an important headline from GM earlier this year where they made a commitment to sell only zero emission vehicles by 2035. Moreover, the Biden administration has made a commitment to replace the fleet of government vehicles with all electric. And the current infrastructure legislation also includes provisions for supporting union-made electric vehicles. On the other hand, sort of in the context of all this seemingly positive news, there are some other issues that underlie perhaps these challenges going forward. And that is around the materials economies and supply chains that will be needed in order to support this large-scale transformation to electrification and renewable energy. So for example, you have headlines talking about an element called cobalt, which turns out to be essential for lithium-ion battery technology. Moreover, lithium itself is also considered to what we will call a critical element in this context. We have reports talking about how 23 minerals are at risk of US supply shortages, and that this situation really is going to require a massive growth and investment in mining in order to support the critical transformation of society to electrification, both in the grid scale and also in the transportation sectors. We also see this in a recent report from the International Energy Agency, which articulated the materials needs for the coming clean energy transition. That just a range of elements and materials are going to become essential that heretofore just did not have the same kinds of markets. So in terms of wind power and solar photovoltaics, you have the expansion of the use of copper, but you also have the growth of other metals that didn't really have a significant role before, things like zinc, rare earth metals, perhaps some have heard of, cobalt, as I mentioned, and also elements like lithium. And we also see this in the transportation sector related to the growth of electric vehicles. So really a new set of challenges where chemistry and engineering are going to play a central role in contributing to achieving these economic targets and also emissions targets in the process to undergo wide-scale electrification. And so what is the other side of this? Well, if in using sort of existing process chemistry for mining and processing of metals and minerals that are going to be important for this transformation, there is a huge environmental burden. Okay, and so that is to say, most of the mining chemistry really hasn't changed very much for 50 or 100 years around attaining a variety of these essential metals for the clean energy transformation. So this is a picture of the Baotao rare earths and iron mine, which is in Inner Mongolia in northern China. This is, as far as we know, this is the world's largest mine tailings lake and a huge producer of purified rare earth elements at that mine. And so there's a tremendous amount of waste effluent that comes out of that process. For example, the production, it has been estimated for the production for 1 ton equivalent of rare earth oxide, there's 10 kilograms of fluoride, 10,000 cubic meters of gas containing chemicals like hydrofluoric acid, sulfur dioxide, and sulfuric acid, so significant acidic wastewater, radioactive materials, and so on and so forth. So this is the environmental burden. This is sort of the underlying cost that you don't hear talked about too much related to the mining and the critical materials that are going to be needed in order to accomplish this goal of electrification. And so this is a huge problem, and this is something that is gaining new attention now, and people are starting to have an awareness of, but it's one, again, which is a tremendous opportunity for science and technology. So in this context, the US and a number of agencies around the world have defined this relatively new term of critical materials. And so critical materials are mineral resources or element resources that are essential to economies and whose supply may be disrupted by inherent geological scarcity, geopolitical issues, trade policy, or other factors. So this periodic table gives you some sense of the collection of critical elements. So elements like I mentioned, like lithium and cobalt, the rare earth metals, niobium and tantalum, platinum group metals. And now, as of yesterday, the USGS has added to this category a couple of new elements, nickel and zinc. So these are elements that make up essential technologies that are critical for, in this case, the US economy in some fashion. And so this is a sampling of some of the technologies that rely on critical metals. As I mentioned, things like electric vehicles, renewable energy. So we have very powerful permanent magnets in wind turbines that are made up of rare earth metals, for example. And so we have a strong connection between rare earth metals and wind power, cell phones and personal electronic devices, as well as solar photovoltaics and lithium ion batteries. And so the other aspect of criticality, so they have a real use and an economic importance. We talked about how there's a strong connection with sustainability aspects. And this is a key component of materials criticality, is that in the Western world, a lot of the work, the dirty work related to mining and production of critical metals has been effectively exported over a number of years to other parts of the world to set up these supply chain imbalances or supply chain issues related to other parts of the world, okay? And so this can be just because of an environmental regulatory climate that we can have materials criticality emerge. Also trade tensions certainly play a role in materials criticality, and also in a wider definition of sustainability around labor practices and the impact that mining and pollution has on local communities. A lot of the world's supply of that element cobalt actually comes from the Democratic Republic of the Congo. And it's understood that cobalt mining there actually supports and sustains conflicts in that part of the world. So there's also a real key people aspect of this problem that's very important. And so it was in this context that myself and this group of dynamic investigators got together a few years ago to try and think about fundamental new chemistry to address these problems. And so we founded what's now known as the Center for Sustainable Separations of Metals. And this is a National Science Foundation supported center for chemical innovation. And the goals of this center are really to develop fundamental new transformative chemistry that can begin to address these issues in critical materials. So we're looking at a range of targets in terms of elements, and we're making assessments of their criticality and then trying to understand, why the mining chemistry is so polluting for a number of these. And if we can develop more sustainable methods to be able to, for example, get them out of ores, but actually also to improve the whole supply chain. We take a holistic view of this problem and also look at the ability to accomplish recycling of many of these critical elements. So recycling is really performed in most cases for critical elements at a remarkably low rate. So we want to understand what the barriers are for that, and also to see if we can develop targeted chemistry, for example, to deliver elements back out of technology. So these are all the goals of the center and things that we've been working towards. So I want to give you a couple of vignettes in this context around some chemistry that we have been developing in the center. And so gold is a really important element in this context. And gold is actually not a critical element, but it's been called a pathfinder element for critical elements because it represents a lot of interesting sustainability issues along the supply chain. And it has a lot to teach us about how we can transform mining and recycling chemistry for a strategic element and apply it in other situations. And so if you're thinking about gold production, there's basically two ways to purify gold from ores or from electronic materials. And one is to use the element mercury, which I'm showing here through this process of amalgamation. It sort of looks like the mercury is eating the gold in this image. But in fact, this is the formation of an amalgam. And this is the technique that is used in many kind of low or small gold mining operations. Another term for this that's used around the world is artisanal mining. This is people in their local communities who are using elemental mercury to try and extract small quantities of gold from gold-bearing materials to sort of make a living for their families. And through the process, they actually heat up the amalgam and volatilize the mercury and extract the gold, having made the amalgam. So you can imagine that process results in a lot of mercury pollution in local communities and mercury poisoning of people. So this is certainly not a sustainable method from a human health standpoint. The other method for gold purification that's practiced on an industrial scale is the use of sodium cyanide. So you can see in this chemical reaction that gold reacts with sodium cyanide in the presence of oxygen. This is the only chemical reaction, by the way, in the talk, to give this metal complex. And this is a very selective reaction that allows for the uptake of gold. But this creates a huge cyanide burden for gold mining. In fact, 12% of the annual supply of sodium cyanide that's produced by industry goes directly into gold mining industry. And there are these tremendous reservoirs of cyanide contaminated water that accompany gold mines in many cases. So there's a famous example in 2000 in Romania of a cyanide spill that resulted in 100,000 cubic meters of cyanide polluted water that were released from a reservoir and caused this massive pollution. So this is dangerous for human health. It's dangerous for aquatic life to have these quantities of cyanide used. So one of my colleagues in CSSM, Professor Fraser Stoddard at Northwestern University, a couple of years ago identified that it may be possible to replace cyanide and mercury for selective separation of gold using a simple compound called cyclodextrin. This is a cyclic sugar molecule that has a very low human toxicity. It's a really benign compound. I mean, it's a natural sugar compound. And what Fraser demonstrated was through a serendipitous discovery that upon reaction of this cyclic compound with certain salts of gold, that this nanostructure emerged where the cyclodextrin moiety sort of snuggled up with the different components of the salt and with the gold in order to create this expanded one-dimensional needle-like structure. And it turns out that that material precipitated from solution. So here was a simple and straightforward way to produce purified gold using a simplified process of precipitation. So within our work in the center, we have built in recent years upon this discovery to improve on the chemistry and demonstrate new capabilities. Let's see if I can get this video to play here. Doesn't look like it. So one of the observations was that for the addition of these simple new organic compounds to gold solution in a similar way could similarly affect the precipitation of gold. And so why is this? Well, this is due to a new approach in sustainable chemistry that is built on the concept of what's called supramolecular interactions. These are not chemical bonding interactions within a molecule, but they're weak chemical bonding interactions between molecules, and they're also quite dynamic. And so these interactions allow for new structures to emerge based on gold sort of snuggling up in its interaction with this organic moiety called a cucubitril. And as a result of that perfect sort of recognition and that snuggling interaction between these two aspects of the structure, you have the precipitation of gold selectively from these kinds of mixtures, okay? And so this is a result that we demonstrated through the efforts of CSSM. And we actually get really nice positive recovery of gold from rather low concentration solutions. So we can get precipitation of, say, a 5 millimolar solution of gold, a rather low concentration, and get very good and effective recovery. Moreover, starting from sort of low gold concentrations to begin with, we're actually similarly able to affect a recovery of the high efficiency recovery of gold using this kind of a method. So this is really encouraging and positive and demonstrates that sustainable chemistry can work in the mining industry. You would think that the gold mining industry would be highly optimized and that the processes would be rather benign, but in fact, they're not. They really are in need of new innovation and ideas in gold mining and in other industries related to mining and recycling chemistry in order to affect positive change. We've also applied the same kind of methodology for platinum salts. So platinum group metals are critical metals. And so we've demonstrated that it's possible to selectively remove platinum from these kinds of mixtures. And so ultimately our goal here is to be able to apply this kind of methodology to recycling of components that contain platinum. So you may have heard of sort of catalytic converter thefts from cars in recent years. And we see sort of increases in that activity every once in a while. And that's because the value of platinum group metals goes really high every once in a while. And so it increases the incentive to sort of have these people to steal catalytic converters, right? But the point is that these critical metals are really going through and have these volatile price changes, which is also sort of a negative as far as the deployment of critical materials in sort of essential technologies. We want to be able to extract and process them in a sustainable way with benign chemicals and have a diversified supply chain that works against these sort of volatile price points in a particular area. So this chemistry works to extract platinum from sort of surrogate materials for recycled three-way catalytic converters. It's not just an academic exercise, okay? We have an industrial partner in this chemistry and in other chemistries called Cyclodex. Cyclodex is a startup company that was founded and registered in 2015. And what Cyclodex has done is they've taken the fundamental discovery that was reported by Fraser Stoddard's group in 2013, and they've really developed it into an industrially viable process for working on a sort of low-grade gold ores. So one can take gold-bearing materials, you can dissolve them with the appropriate salt reagents, and then use that alpha cyclodextrin to affect the precipitation recovery of the gold-bearing material. So this has actually been applied, this technology has been applied at the Comstock mine, the famous Comstock mine from the Old West, as well as sites in Arizona and also in Mexico. So the company has moved beyond a pilot scale demonstration and is actually now a profitable startup company on the basis of this cyclodextrin technology, thanks to support from an SBIR phase 1 and phase 2 grant to the company as well, that has helped allowed for the development of the technology. So this is working. It's working in the real world, and it's not just sort of a flight of academic fancy to be able to contribute to improving and ultimately transforming this industry and creating circular supply chains for not only gold, but a variety of critical metals. I mean, we really want to expand and exploit this technology for other targets, for example, beyond platinum group metals and gold into things like rare earth elements so that they can be isolated with a sort of a fraction of the environmental harm. So I've given you a sense, I hope, of the promise of sustainable chemistry around metal ion separations and being able to support these diverse supply chains. I want to direct you, if you're interested in this topic, to our CSSM website and YouTube page. We talk a lot about the chemistry, the social and political issues associated with critical materials, and also outreach activities like these mining flashcards that we have developed. So there's a whole host of interesting materials that you can find on our CSSM website. With that, David, I think I'll pass it back over to you for the next speaker. I look forward to the discussion.
Dr. Schulte, thank you very much. Very interesting. And let me just repeat that if, for those of you who have questions pertinent to Dr. Schulte's presentation, please feel free to share them in the chat, and we will definitely pose them at the end of the speaking part of the program. It is now my pleasure to introduce our next presenter, Dr. Daryl Mudrow. Dr. Mudrow, a physicist, has spent much of his career operating at the junction of basic research and applied science, having worked in both academic and business environments as a scientist and executive. As a researcher, he has focused in the areas of condensed matter physics and materials science, and he has also served as the founding director of the Office of Technology Transfer at Rice University. His presentation today is entitled Sustainable Sources of Clean Water. Dr. Mudrow, the floor is yours.
Thank you, David. I'm a retired physicist, and I have gotten terribly worried about what I read about the problems of clean water and the availability of clean water around the world. And I begun looking at that problem, and I wanted to present to you some of the problems today, hopefully to bring more visibility for them, and also some of the potential solutions that are in a place and solutions that are being developed. The issue I put here is not too strong a word for the global crisis in water. There is, a lot of the world is now aware of the crisis in climate issues, But the related issues of water availability have not gotten as much visibility as I think it will in the near future. Many of you know of some of the major problems that have existed in water. We're all in this country anyway, aware of the problem in Flint, Michigan, of lead contaminated water being delivered through the water system. River flows are decreasing or vanishing. The Colorado River flow is ebbing. The Aral Sea in Siberia is gone. And so there are so many problems that are putting extreme pressure on populated areas. Just a few facts, please, on the next slide. So this is just some facts that you may not be aware of, that the number of people that really lack access to clean water on an everyday basis is 1 in 10 people on the planet. And in fact, the effect of this is more pronounced on women and girls in the developing world who spend. But you know, there are 800 children every day, children under 5, who die from causes related to contaminated water. So these are problems that we just must get a handle on solving. So next slide, please. Well, look, we need solutions. The world needs the solutions. Solutions are needed on a large scale in urban environments and across entire countries, but they're needed also on small scales on a community and village level. And in spite of what you might think, they're needed in wet and arid areas, in spite of not just the sources of clean water, but the reclamation of clean wastewater to produce drinkable water in return. So the green chemistries that we need to talk about and we need to have people develop are to manage, purify, desalinate, and extract clean water from either saline solutions or from contaminated water in wastewater treatments. Many of the ideas are in the development stages or already in commercial development. Some very compelling ideas with considerable promise, but there's a great deal more that's needed. One that you've probably heard about, most of you have heard about, is a process called reverse osmosis, which is used. After all, we are on a planet where more than half of the world is covered with water, but that water is saline and contains contaminants that need to be removed before it can be made drinkable. Reverse osmosis is a process that uses a semi-permeable membrane to filter out unwanted molecules such as salt or dirt. And it produces drinkable water at the molecular level. So it's pure water that gets produced. But it is a very expensive, complex, and very energy intensive process. It uses a lot of electricity to pressure the water through the membrane. The membrane treatment and development of effective membranes is a continual problem in that business. The pre-treatment of water is also required. Solar energy powered plants are now coming online and are an interesting solution, but there are still further developments needed there. However, the big but that I have listed in red at the bottom is that once the reverse osmosis process is executed and the clean water is extracted, it leaves behind a concentrated brine, which if disposed of in the nearby sea, can destroy the marine life by having an out of balance brine solution in the water. This is an example of a plant that's built in Saudi Arabia. You see the complexity of the plant. This is a very large plant that produces 60,000 cubic meters of desalinated water a year. The plant costs $130 million. It's a sort of evidence of my statement that it's an expensive process. And you can witness the complexity just by looking at the plant. But this is a successful plant. And there are many of these such plants around the world, not just in the Arabian Peninsula. There are plants operating on the West Coast in California, in San Diego and Santa Barbara, and in other places around the world. So this is a very important process. some of the technological improvements that really are needed in the use of reverse osmosis, most important, has to do with the disposal of the concentrated brine. Some activities have shown that the brine can be used as a feedstock to produce commercially desirable chemicals. This has not been developed to a commercial level yet, but the development processes are in progress. Also, the brine has been shown to contain mineable minerals. So much more work is needed to be done here, but I wanted to call your attention to the fact of what the needs are. In new and exciting technical developments, the graphene oxide is looking very promising for the separation membranes. Graphene, as you know, is a recent discovery of in the nanotech world, where carbon atoms are arranged in a hexagonal pattern, connected together, just as shown on the left, a single layer of carbon atoms. If that material is oxidized and laid onto a substrate for support, it has been shown to develop to be an effective filtration filtration medium for reverse osmosis. In fact, companies are already selling this. Lockheed Martin is one company that's selling these membranes. So this is one of the examples of developments that are happening. Now let's move on to away from reverse osmosis, which is a big problem. People are working at trying to extract water from humidity. And there is a great deal of water in the air that can be extracted. And this is where a process that can help on a small scale for people who may need only a few buckets of water a day for keeping their lives happy and safe. And this is a particular example that I think is clever. It's still in development, but it is very promising. It's been developed by Professors Omo Yagi at Berkeley and Professor Evelyn Wong at MIT. It's a new device that uses the devices invented by Dr. Yagi that are called metal organic frameworks. The metal organic frameworks are depicted on the right, where inorganic building blocks and organic building blocks are combined together with a topology in mind, and they form frameworks with cavities in the middle that can store materials or do various jobs. And these are just some interesting pictures. We could go on for an hour talking about these. There are thousands of these that are now have been developed and are being explored for various uses. The ones that Yagi and Wang are exploring are ones that are placed in a box with one surface of the box being black and exposed to ambient sunlight. The MOF that they have developed is hydrophilic and driven by concentration, by temperature and concentration gradients. The water is released from the pores and drips off into a collecting device. So you say, well, that's pretty interesting. How well could this possibly work? Well, there have been examples on the next slide, please. In desert environments and where relative humidities as low as 20% have been shown to collect almost 3 liters of water per kilogram of metal oxide framework material. They operate passively without any power input aside from ambient sunlight at a flux of less than 1 sun. So you can see this could work once it's all of the manufacturing issues are out of the way. It could work in providing small amounts of water for village and community purposes. There are others who are pursuing similar goals. I don't have time to go into all of them, but just mention a company called Genesis System in Tampa, Florida. It's working on another nanotechnology-based solution to capture water from humidity in air. So this is a promising development that I want people to know about. Well, let's switch to wastewater. This water, we've been talking so far about producing water from the sea or from the humidity in the air, but water gets, after it's being used or being in industrial processes or for use in cooking or whatever, is no longer drinkable or potable as clean water. wastewater treatments are widely practiced across the developing world. Most cities have a wastewater treatment plant, and the treatment plant screens and sediments the solids that are contained in the water that's being treated, and is further filtered through sand and fabric filters and carbon to remove impurities by chemical absorption. And then the microorganisms metabolize the organic matter biologically. So it's a complex process, and I don't want to go through all of the details of it, but it is working and working very successfully throughout much of the world. So next slide, please. So it treats sewage runoff, raw sewage, rain runoff, industrially used water. Depending on the purpose, the water is commonly returned to rivers after treatment. So it's essential that the water be clean enough to be returned to the rivers and be reused in the water cycle. Today, however, one of the things, interesting development, particularly in the area of architecture, is that architects are looking at collecting and treating wastewater on site for developments that they are designing. It's becoming more common, more necessary, and more complete. Even returning treated sanitary waste to drinking systems are working and being used in commercial sites today. We know that it works for astronauts, and they're bringing these down to Earth, and it seems it can work. One of the main problems that those people face, and I think one of the reasons I brought it up here today, is so that people can be aware of this issue. Regulatory bodies and local permitting agencies need to review the architect's plans, and the agencies who do this judging lack experience with things like treated sanitary waste for drinking systems. And the easiest solution for them is to say no. So the architects have a large uphill battle in trying to get these plans in building. And the next slide, please, is just an example of a successful innovative solution in this area of wastewater treatment. This one at the East Bay Municipal District in Oakland, California. The wastewater treatment there is actually a green factory. They combine wastes from sewage, food waste, grease from local restaurants, wastewater streams from wineries, poultry farms. They're all mixed together, and they're digested by microorganisms designed to produce a biogas. The biogas is captured and provides the power that operates the wastewater treatment plant. So you can see there's a significant amount of progress in the wastewater treatment, but it needs to be expanded and applied in other environments that are less well developed. The next slide, please, opens an area that's probably occurring to all of you as listeners, like, what about the problem of water in agriculture? We've heard a lot about that in the tree farming for almonds in California, using huge amounts of water and so forth. I don't have time to even begin to document that, but I do want to introduce to you a very promising area of agriculture that is beginning to take shape in this country and in some areas of Europe, where empty spaces in urban areas are being converted to vertical farms. Shelving is built with piping systems that can pump hydro solutions to the roots of plants. Artificial lighting is used, and it's controlled electronically, both time and color. It requires energy for the pumping of lighting and solutions, but it's producing vegetables close to the consumer with less transportation costs, lower time to delivery, so the vegetables are produced on a fresher scale, and it provides urban employment opportunities. This is a nascent industry that is growing very rapidly. There are a number of companies around the world that are beginning to develop this. We had a program on Science History Institute just a month ago on this, where 4 companies were talking about their progress. And I want to call your attention to it because it's a very promising possibility. The other problem that's associated with water treatment and with sustainability of clean water is the enormous political and economic issues that are associated with it. Obviously, it's going to cost a lot of money to put things in place to provide water for everyone who needs it in every environment where it's needed. And the question of managing those costs will be difficult and not so easy today in today's political and economic environments. However, and just to show you, for example, even in places where water treatment has been in place for a long time, especially in older cities, there are major costs and political issues associated with it. The lead-containing piping in Flint, Michigan that I mentioned earlier is one of them. In our case here in Philadelphia, where I'm sitting, there is Philadelphia, next slide please, is very proud of being one of the early providers of water treatment systems and water to its citizens through piping and water treatment plants and wastewater treatment. The system is now quite old. This is an example of a break in a 30-inch water main that broke about 3 months ago at a few blocks from here on 6th and Bainbridge Street. It was a 100-year-old water main made out of cast iron, and the difficulty of replacing a 30-inch pipe that's carrying huge amounts of water is not an easy engineering feat. They've been working on it now for several months. I see that now as I walk past there that they're making progress on trying to insert another pipe inside the older pipe that was broken and that may rupture further. But the engineering and the cost associated with this was not one that was necessarily anticipated. And there are other examples of the same thing actually happening here in Philadelphia. So the broadening of the awareness of this climate change, of this water crisis, is as important as in the climate change. You know, Biden commented at the COPD meeting that Professor Shelton mentioned, was that the single most important thing that's gotten attention of the world is climate. But the message does not adequately frame the water crisis, which is just as important, particularly for the health of people who are deprived of water or who are being affected by contaminated water. So the media will certainly begin to get the message and begin to project this. There will be the case of naysayers, of course, and that is going to be an interesting thing to see how it has to be managed. And these are only a few of the societal adjustments that will be needed to bring this problem under management control and have healthy water for everybody across the globe. Thank you very much, and I'll be happy to answer some questions when we get to the period of questions and answers at the end.
Well, Dr. Mudrow, many thanks. Certainly a topic that's very much in the news these days, as you note. I am now delighted to introduce our next presenter, Dr. James Bateas. Dr. Bateas is the Wayne Goodman Professor of Chemistry and Professor of Materials Science and Engineering at Texas A&M University. Dr. Bateas is an expert in materials chemistry of surfaces and interfaces, with research activities spanning a broad range of fundamental surface and interfacial phenomena. His research in tribology focuses on the bridge between chemistry and mechanics, where his lab conducts atomic force microscopy studies of atomic scale friction and wear of oxides and 2D nanomaterials. He recently extended this work into fundamental studies of mechanochemistry and now directs the new National Science Foundation Center for the Mechanical Control of Chemistry. He has been recognized twice by Texas A&M for excellence in teaching, receiving Association of Former Students Distinguished Teaching Awards at both the college and university levels. And he was elected a fellow of the Royal Society of Chemistry in 2012. His presentation today is entitled Mechanochemistry, Catalyzing the Future of Sustainable Synthesis. Dr. Bateas, welcome.
Well, thank you very much, David, and I really would like to also express my gratitude to the Chao Foundation for supporting this wonderful symposium. And I'm happy to be here today to talk to speak to everyone about some thoughts about mechanochemistry and kind of our vision of the impact of mechanochemistry for sustainable chemical synthesis. Mechanochemistry actually spans such a broad area. It's impossible for me to kind of cover and touch on all of the topics, but I want to highlight a few aspects and some potential opportunities for really sustainable chemical synthesis using mechanochemistry. So first, I just want to start off with talking about, well, what is mechanochemistry? Well, mechanochemistry is the application of mechanical force via shear, tension, compression to molecules to drive chemical transformations. And so, we often think about doing chemistry in beakers and mixing solutions and having molecules react in that way, but mechanochemistry is actually fairly ubiquitous in many different places. And this includes, touch and sensing. So mechanotransduction, when we feel touch or compression, there are chemical transformations that occur in response to that. As was mentioned in terms of controlling friction at interfaces, or in tribology and tribochemistry, sliding interfaces actually change the chemical constituents that are in between those sliding contacts, altering and controlling the friction of those interfaces. In foods, grinding of things like corn and meals or other types of food products, which are then ground or sheared or shaken, you can actually have chemical transformations that occur in there. But today I really want to focus on the use of mechanical force to actually drive and direct chemical synthesis and its opportunities for green and sustainable chemistry. So in 2019, mechanochemistry was actually named one of the top 10 innovations that would change the world by the International Union of Pure and Applied Chemistry. And mechanochemistry, I just want to point out a couple things. It allows some processes that are not possible in solution syntheses to actually occur. And moreover, in many cases, since mechanochemical reactions can be done under dry conditions, it allows you to achieve these processes in solvent-free conditions, thus offering substantial benefits in terms of both green chemistry and sustainability for these react processes. There are still challenges, though. We're still struggling to understand exactly how this all works on the molecular scale, and this impacts basically how we then define and set up and carry out mechanochemical reactions. But I think the future is bright, really, for these activities. So in terms of being a sustainable technology for synthesis, I just want to point out many of the factors of mechanochemistry that actually enable and help it support the 12 principles of green chemistry. One, which I already mentioned, is the fact that mechanochemical reactions can often be done under dry conditions. So you can take your reactants and you can put them together and grind them together and carry out the chemical transformation in a solvent-free environment. So you don't have to be really concerned with then dissolving something up and then having to remove and extract that solvent later after to isolate your products. In many instances, mechanochemical reactions have been shown to take far less time, to have increased yields over solution-based processes, and increased selectivity through the appropriate choice of the application of mechanical forces. Many times, these reactions can also be carried out at lower temperatures, so it consumes less energy. And in terms of this, in concert with the increased selectivity, this also reduces the amount of side products that might have to be isolated from these systems. So as I mentioned, in many of these places, this then basically allows us to actually meet many of the principles of green chemistry, in that without solvent, we reduce waste because we have increased selectivity and yield. There's atom economy. Without those solvents, reactions can be less hazardous. Systems in which you would normally have to dissolve some types of materials, even if the compounds may not be initially benign, the fact that you may not have to actually put them into solvent can also make them more benign from those aspects. They save energy, they're renewable. In many cases, if solvent is used, it can be done actually with water. And it reduces both degradation, pollution, and then overall making these processes safer for the environment. So mechanochemistry is actually one of the oldest forms of doing a chemical reaction. So mechanochemistry was actually first mentioned in the literature by Theophrastus, who demonstrated the grinding of cinnabar with acetic acid in a copper vessel to actually extract mercury from that reaction. So using kind of a mortar and pestle type process to do that. And later Faraday also illustrated this process, showing that you could actually isolate silver through the reduction of silver chloride by grinding it with zinc. And in his work, this was clearly a well-known method of doing chemical reactions at the time, because in his work, he actually referred to this method as the dry method of chemical synthesis. But it wasn't really until the late late 1800s that M. Carey Lea really put this into practice and talked about how clearly mechanical force can bring about reactions in the same way that light, heat, and electricity can supply energy to a reaction to help drive it. And so M. Carey Lea is often thought of as being the father of mechanochemistry. Now, of course, doing reactions using mortar and pestle, that's a simple way to carry out those processes. But in terms of scaling this up and carrying out larger scale and broader scopes of reactions, I want to introduce you now to some of the more common methodologies that are used at the laboratory scale and on up. One of the predominant methods is what's referred to as ball milling. And in ball milling, you have a reactor vessel, and this reactor vessel can be made out of different types of materials. And you have metal or ceramic balls. You have your reactant materials. You're going to put this inside this reactor vessel and seal it up, and then basically shake it. And when you're shaking this, you can then actually have shear and compressive forces that are then acting on the components in the vessel, carrying out the overall process for reaction. And then the reaction is then completed, and you can remove and isolate your product. Now, there are many different tools of the trade, however, for carrying out mechanochemistry. That one that I just illustrated there is this mixer mill, a mechanical chemical shaker. There are also planetary mills in which similarly you have a metallic metal vessel in which you're putting balls inside there and you're kind of shaking this around as it's rotating around on the mill. Both the mixer and shaker mill and the planetary mills are batch processes. And the typical types of reactions there you're going to be carrying out in terms of scale range from milligram to up to maybe kilogram scale for those types of systems. As we think about scale up of these types of dry chemical reaction processes, other types of tools also begin to come into play. One that is well known is what's called twin screw extrusion. And when in a twin screw extruder, you have basically a hopper here in which you're going to put your feedstock into there. And it's going to be carried through and conveyed by these twin screws. So there are going to be conveying components and then kneading components, which are going to be basically introducing shearing of the material that's being drawn through this, as well as compression in these kneading components. And then your product will exit out the other side. This is a continuous process, which allows you then to access large scale production up to kilograms per hour. And then a newer tool that's now being implemented also for looking at these systems, which you don't even have to include, for example, like a ball inside of a reactor vessel, is acoustic mixing. And in an acoustic mixer, you're then actually acoustically resonating the entire vessel at its resonant frequency. And then the shearing and compressive forces then acting on the reacting components in there is what helps drive the reaction. This is again a batch type process, but allows you then to also access gram to kilogram types of production. So really, when we think about mechanochemical reactions, it's really out with the old and in with the old new, which is that we're going back to these types of dry methods for chemical synthesis because of many of the advantages that they have in terms of eliminating some of the needs that you would typically have in solution-based processes. So in a solution-based method, you might have to heat the system up. You have to find solvent that can actually dissolve not only your reactants, but actually have your product soluble in there in many instances. You then have to eliminate that solvent and purify and remove that to obtain your final product. In mechanochemical methods, as I mentioned, in many cases, these systems can be run at ambient temperatures. The reaction times can be much shorter. In many systems, these can be solvent-free or require only minimal solvent to carry out reaction, which is then going to also reduce the amount of waste that's going to be produced, removed, and reduce the amount of time that you have from reactant to product. So, one thing we kind of think about in this area is that it really kind of this dogma of like dissolves like, where you have to have something that you can put your reactant to and then get your product and then get your product out of, really can be broken down using mechanochemical methods. I just want to illustrate a few large examples of mechanical chemical syntheses. Again, as I mentioned, the literature is replete with so many examples now where this is coming into play and showing its capability. One example I want to illustrate here is ammonia synthesis. So ammonia is normally synthesized using the Haber-Bosch process. in which you have a catalyst bed and you're flowing gas, gaseous nitrogen, hydrogen over that. Normal synthetic process that occurs at around 400 to 500 degrees C at high pressures of, say, up to 100 bar. Mechanically, it was recently demonstrated that this process could be done mechanically in a ball mill, basically by grinding iron powder in the presence of nitrogen and hydrogen gas. This process could be run at 45 degrees C, or what might just be a really hot day in Texas, and at one bar. So really a significant energy savings in terms of the amount of energy that would need to go in to actually get to these high temperatures. Another system, as we just recently heard about, is our metal organic frameworks. These have been demonstrated for types of water trapping and separation, but they're also quite viable for different types of gas storage and separations. Metal organic frameworks form these organized structures, and in the normal synthesis for many of these types of compounds, you require stabilization with an organic solvent. So in this particular case of this zirconium moth, the normal solvent that would be used would be dimethylformamide. Mechanically, it was shown this could be synthesized using only a minimal amount of solvent, following a process called lag or liquid-assisted grinding with just minimal water. Similarly, in zeolites, by using the dry method, by using mechanical ball milling or other types of milling processes, you have facile transformations of both pre and post treatment of the material. So you can use ball milling to just grind, activate the material, obtain the appropriate particle size that you want for those materials, and then in post processing of that, finalizing and isolating the different types of zeolite structures that you want. From an economic standpoint, there was an economic analysis done recently from one of the labs in Berkeley, kind of looking at, for example, the synthesis of one of these metal organic frameworks, this magnesium containing moth. This baseline cost was the estimate using the standard synthetic production procedure for this moth, based on the cost of materials, the amount of solvent used, everything like that, and scaled basically to the cost per kilogram. And you can see that in the baseline conditions, this was costing around $70 per kilogram. Doing this mechanically using liquid-assisted grinding, that cost could be dropped to only a little over $12.50 per kilogram. And here again, I want to point out one of the major advantages of mechanochemistry is that if you can eliminate, by and large, the solvent needs, then you don't have to worry so much about using it, isolating it, storing it, and then recovering it or recycling it. And so that's going to be a significant cost savings that can be realized in terms of these synthetic methodologies. Similarly, in the synthesis of pharmaceuticals, mechanochemistry is starting to show significant promise. This is one of the first examples of the synthesis of pharmaceutically active compounds. Was the synthesis of these anti-diabetic drugs. And in this process, again, this could be done in a completely dry type of condition. Or the synthesis of various types of active pharmaceutical ingredients or APIs. In this reaction system done using squint-root extrusion, it was recently shown that the space-time yields, or basically the amount of product that you could produce per day, was significantly magnified when using a mechanochemical reaction process versus using the solution-based process, going from roughly 430 kilograms per cubic meter per day to up to 68,000 kilograms. So there are possibilities already in existence now for scale-up of utilizing these methodologies. And then I just want to come back to one of the areas that we mentioned before, which is that mechanochemistry is also important in controlling friction at interfaces. Friction and wear have a near ubiquitous impact on many sectors of the economy. Anything where you have moving parts and gears, you have frictional wear, and energy losses in there. And in fact, it's been estimated that 20% of the world's energy consumption goes into nothing but combating friction. And in terms of economic impact, it's estimated to be roughly on the order of about 1.5% GDP in countries. So that's about $350 billion per year in the US lost to friction. And as we start to think about new and emerging technologies, whether they be for electric vehicles or for space flight or for micro devices that you have to control friction in, having chemical constituents that can actually control and modify those frictional properties become important. And so, you know, you might be asking, well, what is the relationship between friction and mechanochemistry? And a lot of this comes back to the types of processes that occur in sliding contexts. One of which is the formation of what are called tribofilms. So in many instances, lubricant additives are included in lubrication-based systems. And it's been shown that only under compression and shear, you actually form these types of low friction stabilizing materials. And understanding why they form or the choice of materials to get them to form, I think is a significant challenge for the mechanochemical chemistry community. And so we ask the question, you know, can expanding the portfolio of mechanochemical syntheses we actually use as a way to guide the synthesis of new materials for controlling friction at interfaces. And so this really brings us to one of the key elements, that we set out in terms of forming our NSF Center for the Mechanical Control of Chemistry. So as David mentioned at the beginning, this is a new NSF Center, and this is a partnership between Texas A&M, City University of New York, MIT, UPenn, UC Merced, and McGill University. And we're trying to ask the fundamental challenges: can we make mechanochemistry more predictable? So we have tools and capabilities of enabling scale up, but we need to be able to connect the dots between what happens on the atomic and molecular scale to actually what the macro scale synthetic outputs are to develop this into a reliable and predictable chemical synthetic methodology. And so we're kind of the new kids on the block. However, if you want to learn more about mechanochemistry, you can go, of course, to our website, but there are other global efforts in this. First of which is the International Mechanochemical Association, or the IMA, which was established in 1988, and it's an affiliated institution with IUPAC. There's also a large global effort in mechanochemistry for sustainable industry being run out of Europe. So this cost action, being led by Evelina Colacino, actually has 41 participating countries and nearly 130 researchers participating in this program. And it's developing many different types of educational, scientific, and training programs to help enable the scale up of mechanochemistry and its translation into sustainable technology. So eyeing the future, there are various things that we can think about. You know, how do we actually enable this? New tools for controlled forces in ball milling and extrusion will be important. Having ways to monitor and control precisely the forces that are acting on the reacting compounds. Having ways to actually monitor the spectroscopically, for example, what's going on in reaction processes will be important. And then we also think about other things that are far out there, like mechanochemistry in space. Why not? You know, if you're thinking about, doing chemical reactions on other planets, it's going to be very difficult to carry all the materials that you need with you. So since you can carry out mechanochemical reactions without solvents, or maybe with minimal solvent or things just like water, this can be a safer process for carrying out those processes. So imagine, for example, doing mechanical reactions just using lunar or Martian dust to make catalysts out in space. And so if you want to learn more, as I mentioned, I can't possibly cover all the different areas that mechanochemistry is impacting. We've been fortunate to work with the Science History Institute on developing a Google Arts and Culture exhibit on kind of introducing the history and the direction of mechanochemistry. And I'd also like to point you to our YouTube channel, the CMCC Mechanochemistry Discussions, where we've had world-recognized experts in many different areas of mechanochemistry come and talk about their view of these different aspects of synthetic methodologies for utilizing mechanochemistry. And with that, I'd just like to acknowledge and thank everyone. And David, I'll turn it back over to you.
Very good, James. Thanks so very much. And now I'd like to introduce our final presenters, Drs. Naomi Hallis and Mr. Trevor Best, the co-founders of Syzygy Plasmonics. Naomi Hallis is the Stanley C. Moore Professor of Electrical and Computer Engineering at Rice University, where she also holds faculty appointments in the departments of physics and astronomy, chemistry, materials science, and nanoengineering and bioengineering. She is the author of more than 350 refereed publications, has more than 20 issued patents, and has been elected to the National Academies of Sciences and Engineering, the Royal Society of Chemistry, and the American Academy of Arts and Sciences. Trevor Best is the founding CEO of Syzygy Plasmonics. Before starting Syzygy, Mr. Best worked in management at Baker Hughes, where he applied his expertise in quality assurance, regulatory compliance, technology development management, supply chain management, and business process architecture. With Syzygy, he has successfully raised 3 funding rounds and is currently focusing on bringing Syzygy's revolutionary photochemical technology to market. Title of Dr. Hallis's and Mr. Best's presentation is Nanoparticle-Based Photocatalysis for Sustainable Industrial Chemistry. Welcome to you both.
Thank you very much. First, I want to thank you so much for the invitation to speak at this symposium. And I also want to thank you for just being able to attend and hear those. So every exciting talk that we've heard is truly a frontier in chemistry. So I'm really happy to join you on that front and to tag team with Trevor Best today to talk about some innovations that developed in our laboratory and how they have moved very rapidly now into technology and commercialization. This is my, sorry about that. This is my title slide, and I would like to, so our work involves metallic nanoparticles, and these are the various elements of nanoscience that have existed. Gold nanoparticles are a great example. They have been around for thousands of years. This is the rose window in Chartres Cathedral. And the beautiful red in this stained glass window is actually composed of gold nanoparticles embedded in glass. And the alchemists developed ways of making this long before they understood the redox chemistry of gold nanoparticles, or did they understand why nanometer scale gold particles did not look gold at all, but instead absorbed green light and therefore transmitted the complementary color. So it even existed in Roman times, but it took Michael Faraday, whose name has already come up in this symposium, as a tremendous pioneer of chemistry. So clearly he was pioneering in mechanochemistry, but he also pioneered our understanding of how light interacts with gold nanoparticles. And he was a great public speaker, so he used to carry a vial of gold nanoparticles, a little solution, in his pocket when he went to give public lectures. And there's a picture of that same solution, which is in the British Museum of Science and Technology, and it's known as Faraday's colloid. So gold nanoparticles, because they're metals, have a very important property. So gold, silver, copper, aluminum are all examples of metals that interact very strongly with light. So when a light wave hits a gold nanoparticle, it will drive the E field of the electromagnetic wave will drive an oscillation of the electrons with respect to the positive ion background. So you excite an electronic wave. This wave is called a plasmon. It's localized like a standing wave when you're on an isolated nanoparticle, and it can and the interaction is very strong. And because of this is a very active way to mediate nanoparticle processes. So upon light excitation, the light energy can dissipate as heat. And so these particles are responsible for very intense photothermal effects. But also when the plasmon is excited, it can decay by energizing hot electrons with the same energy as the plasmon itself. So if those electrons, those energetic electrons can transfer into, for example, the lowest unoccupied molecular orbital of an adsorbate sitting on the nanoparticle surface, then you have charge transfer, and that can facilitate chemistry. So there are certainly, so photothermal applications are very important, or an important mechanism by which we use gold nanoparticles or plasmonic metal nanoparticles, but also photocatalysis, which is the focus of our talk today. So this is one theme of all of the discussions of all the talks today actually has been energy. And one aspect of the chemical industry that is maybe not a necessarily a banner of pride, but it's certainly a banner of reality. And that is that the bulk chemical industry consumes a lot of energy, and a lot of the cost of chemicals is the energy that's used in their synthesis as well as in their separation and purification. So it would be wonderful to develop new ways to do chemistry that don't require the very high temperatures and pressures often that are used in chemical synthesis that carry over into the chemical industry itself. And so this is where plasmons come in, as I mentioned just a moment ago. As you excite this collective electronic oscillation or a plasmon, it decays by generating hot electrons. Those hot electrons could transfer into an adsorbate molecule sitting on their surface, and this induces, of course, a transient negative ion state. And that transient negative ion state can undergo dissociation with a much reduced barrier relative to a neutral molecule. So this is a way to induce chemistry using plasmons. And here's a very simple illustration of this property. So what we're going to do is dissociate hydrogen. So if we take hydrogen and we flow it along the surface of a gold nanoparticle, so hydrogen is a very inert molecule to dissociate. It's basically isoelectronic to helium. So it requires a lot of energy to dissociate it. But if we flow it along a gold surface and then we excite the surface plasmon, then the surface plasmon can inject an electron into the H2 molecule, converting it, of course, to H2 minus. H2 minus has Coulomb repulsion, and this results in dissociation of the hydrogen molecule, essentially at room temperature using visible light. So this was one exciting reaction to see that we can use light as a way to do chemistry in a very simple way where there's no side reactions and we can clearly see what's going on. But of course, gold is not that chemically active. So if you, of course, for light, we focus on the noble metals, on the plasmonic metals. But if you do catalysis, you don't consider these are particularly catalytic at all. So people who do catalysis are interested more in the transition metals. And of course, as was mentioned earlier, the platinum group. So these are metals that have stronger binding affinities with adsorbate molecules, but they're poor plasmonic materials. They rarely, if ever, interact with light, or if they do, just very weakly. And so we thought, maybe there's a way to combine the best of both worlds. We could use a plasmonic nanoparticle to capture light, but then also on that plasmonic nanoparticle attach little reactive sites that we call reactors. So if we put this whole complex together, we call it an antenna reactor. So the nanoparticle captures light, and then we have reactive islands on the nanoparticle that will now be optically active because they're sitting within the fringing field of the nanoparticle itself when it is illuminated. So we've demonstrated this idea of an antenna reactor. So you can put little metal islands on the outside of a nanoparticle. You can also grow several other types of things like, for example, MOFs, for example, or semiconductors like copper oxide. And you can try several different types of metal islands, even single atoms. And so we've demonstrated several different types of chemical reactions that all can be driven by this antenna reactor complex. So there's one particular reaction that is of tremendous interest to industry. So methane dry reforming, or methane reforming generally, is the industrial method for producing hydrogen. So CO and hydrogen together are called syngas, but certainly if you want to mineralize the CO, you can mineralize the CO, and you can also then harvest the hydrogen for fuel for hydrogen vehicles and other hydrogen driven types of systems. So this is a very endothermic reaction. You have to put in a lot of energy. Traditionally, this is done at very high temperatures in industry. And also the catalyst surface themselves will actually bind multiple carbon atoms, which will polymerize, and that will actually just poison the catalyst. And so we thought, well, let's see if we can build an antenna reactor with that same type of with the same type of affinity for the reactants for methane and CO2. Of course, those are two greenhouse gases that it would be very nice to get rid of, and drive this reaction with light instead of heat. And so, in fact, this works extremely well. So the reaction works actually using antenna reactor nanoparticles at temperatures that are more than 500 degrees below what is typically used in industry, really about 300 degrees Celsius. The selectivity for photocatalysis is much, much higher than the selectivity for thermocatalysis. Essentially, the reaction runs without any side reaction, back reactions, and the photocatalytic energy efficiency is extremely high, 35%. And so we can think of, so this is where syzygy comes in and where Trevor comes in. So this is, if we think of building a reactor that's driven by light instead of heat, you know, if you had a choice, you'd want to always do this by light, because the light energy enters the light energy is concomitant with the reaction barrier itself. So it's easy to make the reactions happen at much lower temperatures. Having reactions run at much lower temperatures means the reactor itself can be built with much less expensive materials like aluminum instead of high alloy steel. And of course, we can think about, since the temperature is much lower, we can think also about running the reaction, not with fossil fuel itself, but actually with electricity, because we can then use basically light-driven solid state lighting sources to drive the reaction itself instead of fossil fuels. So this is the basic idea of an antenna reactor. These are some of our collaborators for the last several years working on the antenna reactor concept. And now I'd like to introduce Trevor Best and Syzygy Plasmonics, and he will talk to you about how this idea now has transitioned into commercial realization.
Awesome. Thank you so much, Naomi. It is a pleasure to be presenting to everyone here today. There we go. Fantastic. So, as Naomi mentioned, we are developing, photocatalytic reactors, and to really understand what it is that we are doing with Professor Hollis's technology, I would like everyone in the audience to take a step back and think about planet Earth and how planet Earth operates today. And what you'll see is that the trillion-dollar chemical value chain is really this foundation for modern society. And a few raw materials, petroleum, natural gas, and air go on to create many different things. Petroleum feeds the value chain for a class of chemicals called aromatics. Natural gas feeds the olefins value chain, as well as produces hydrogen for methanol and ammonia. And these value chains go on to form the raw materials for everything that you see around you right now. Textiles, pieces of houses, pieces of cars, so on and so forth. And what you should know from all this is that this value chain is really, this value chain is really driven by combustion. And so, combustion to produce these molecules and drive this value chain is responsible for more than a gigaton of carbon emissions every year. And this is where Syzygy Plasmonics comes in, using the technology that Professor Hollis has developed. And so we are developing a completely new type of chemical reactor. Our reactor, based on the antenna reactor photocatalyst, is fundamentally different than every other chemical reactor on the planet right now. And it completely eliminates the need to combust fossil fuels to power those reactions and drive that chemical value chain. What it is doing is it replaces that combustion of fossil fuels with light from LEDs and renewable electricity. So at the end of the day, we are using Professor Hollis's technology to electrify chemical production and allow this industry to operate using renewable electricity, which supports our vision of driving a gigatons of emission reduction by 2040. Now, eliminating emissions is great. And apologies, I'm still learning how to master the controls through Zoom. Eliminating emissions is great, but really it comes down to cost. And on the left, you'll see a traditional thermal reactor. You're burning fossil fuels to produce high pressure, high temperature that's needed for traditional catalysis. But what this means is that you have to build these traditional reactors out of very expensive materials, things like nickel and chrome. A good example is Incalloy 800HT, which is $42,000 per ton. Also being driven by fossil fuel inputs, the operating costs are projected to increase as carbon pricing comes online, carbon taxes increase cost, etc. In contrast, Syzygy's reactor, which is shown on the right, is going to be much lower cost. At the reactor wall, where the LEDs are, it is actually room temperature and atmospheric pressure. This allows us to build our chemical reactors out of materials like aluminum and glass and plastic, which are much, much lower cost. And the operation is being driven by renewable electricity, whose cost is trending strongly downward. This is a trend that we are very happy to ride to success. So, of course, this technology is made possible by the breakthrough innovation. This is the antenna reactor photocatalyst. It is the most active and stable photocatalyst in history, developed over, really, if you look at it from the beginning of their plasmonics research to today, you're looking at 30 years of development, through Professor Hollis's incredible work. It has been highly validated. It has been published multiple times in Nature and Science, and those papers have helped Syzygy win grants from the United States Department of Energy Advanced Research Projects Agency, as well as grants from the National Science Foundation. By far the most interesting aspect of this technology, though, is its platform nature. Naomi talked about one reaction, dry reforming, but that is just one of many, many different chemical reactions that we have been able to do using her technology. It is broadly applicable to many different chemical reactions, and this is exactly what we're doing. So, I'm pleased to announce today, this fossil-free vision of that trillion-dollar chemical value chain that this technology enables. Green blocks are reactions that Syzygy is actively working on today and actively preparing to take to market today. Market entry for the purple blocks will come sometime later on after 2025. What you see on the left that really makes this unique is that we are starting this value chain by repurposing greenhouse gases as feedstocks. The two most potent greenhouse gases, CO2 and methane, feed the production of our primary molecules, hydrogen and CO, which then go on to feed the production of the secondary molecules, methanol, ammonia. And through these basic raw materials, we are able to plug into the foundation of those value chains that go into building everything that we talked about earlier. And, the trillion-dollar chemical value chain aside, these molecules here are also being targeted to feed the trillion-dollar fuels value chain. So the amount of potential impact from this technology is truly tremendous. So the four reactions, we showed you all those four blocks, specifically the four reactions that Syzygy is working on commercializing today. So the four reactions we have taken out of Professor Hollis's lab and that we are actively working on getting into the market are shown here. On the left, you see the carbon negative pathways, where we are taking in those greenhouse gases of methane and CO2 and turning these into hydrogen and methanol. When combining these two processes of photocatalytic steam reforming and photocatalytic dry reforming together, you get a novel process that we are calling double reforming, where you are making hydrogen and methanol from methane and water and electricity. The economics of this are looking to be especially good, and we are getting a tremendous amount of customer interest on this. On the right, you see our zero carbon pathways that are based around ammonia, where we're both synthesizing ammonia and splitting it again to get the hydrogen back out. So both of these reactions are critical to the future ammonia value chain that's being established around Asia. Apologies. Sorry. So when you look at our scale up, it looks something like this. And to better understand, where we're going, and what our scale up looks like, you can see, like in the beginning when we started, we were making like milligrams of hydrogen per day, and it was taking like megawatts of energy. And from there, we've applied basic engineering principles, optics, electrical engineering, chemical engineering. We started making our basic small cell reactor that made about 100 grams of hydrogen per day at about 68 kilowatt hours per kilogram of hydrogen. We used that data to raise $10 million. With that, we kept advancing the technology, to a kilogram per day, energy consumption continuing to come down. That 10 cell reactor data, we actually used that to raise $24 million. And since then, we have started working on the large cell reactor. The large cell reactor today is making about 5 kilograms of hydrogen per day at an average of around 30 kilowatt hours per kilogram. What's truly phenomenal about all this is this represents approximately 500,000x scale up over the past couple years. So this is just a really, really tremendous scale up, and it is a testament to how good the technology was coming out of Rice that we have been able to move this quickly. You know, because the catalyst is pretty much done. You just have to build a chamber around it that works. And where we're going, you know, finalizing our commercial reactor design next year. This is the platform reactor that's going to be able to do all those different reactions by simply changing out the catalyst. You know, starting with hydrogen next year, we're going to be making about 200 kilograms of hydrogen per day per reactor. And moving forward beyond that, we start to package it for any size that industry needs, and eventually getting into mass production around the middle of the next decade, with around 10 to 15 kilowatt hours of electricity consumption per kilogram of hydrogen. And that will equate to about 70% energy efficiency. Altogether, you know, the big thing to remember here is that we really only need to scale up about 40x from where we're at to go into the market. And we've already secured capital to do that. And you know, are getting well into the detailed design for this reactor. After we go to market, this is what it starts to look like. Here we plot our electricity consumption versus one of our main forms of competition for hydrogen, electrolysis. They need around 50 kilowatt hours per kilogram, and we're already blowing past them. You know, when we achieve our goal of 10 to 15 kilowatt hours per kilogram for hydrogen, that cost target of $1 per kilogram that you know, many people are really excited about for hydrogen starts to become very, very possible. And we also mentioned you know, lower capex. So this shows you what's possible when you can build your reactor out of aluminum. This chart's based off Wright's law and shows the projected future costs for our reactor, assuming certain learning rates. So the red lines represent the cost of hydrogen reactors today, the top one for small distributed reactors, and the bottom one for larger centralized reactors. If we learn at an average pace, that's the blue line, then we do really well. If we can learn quickly, like let's say at the same speed as the solar industry, then we end up beating incumbent technologies on CapEx by 50% or more. You know, we've got really incredible traction together with world-class investors who've raised close to $40 million. We're using this to deploy our pilot early next year. We've got more than 2 years of cash on hand, supported by really fantastic investors, including strategics who have invested in us to deploy our technology in their refineries. We have a really strong management team that's making all this happen. You know, together we've got the experience and the know-how to disrupt this industry and achieve that fossil-free vision of the future that I laid out earlier, especially, you know, with technology as strong as what's come out of Rice. You know, it's lots of potential in the future and the right team to go achieve that. And yeah, I'd just like to end by saying thank you so much for taking the time. I believe that I'm the last presentation of the day, and it is time to transition into Q&A, and I would love to answer any questions that anyone has about our technology.
Very good and very exciting stuff. And Dr. Hallis, Mr. Best, thank you so much. And my thanks to all of our presenters today for introducing us to the challenges, yes, but especially the opportunities presented by the different sustainable chemical research and innovations in the respective fields that they discussed. And as far as Q&A goes, Mr. Chao will not be able to join us in the Q&A today, but our 5 presenters have graciously agreed to take questions, which I see many of you have been sharing via our chat as we've been going along. And I think I'd like to start the Q&A where we began, with a question for Dr. Shelter. Dr. Shelter, this question comes from Kwame Wusu, who asks, what other materials have been investigated for the sustainable recovery of these precious metals?
Yeah, so Kwame, I really appreciate the question. Thanks for your attention and your interest. I mean, we're approaching this problem from the standpoint of sort of chemical philosophy and the fundamentals of what kind of chemistry that we can develop to address this problem. So what I shared with you was one vignette where we were doing supramolecular chemistry to accomplish the separation, and that involves taking these organic compounds and combining them in metal-bearing mixtures to see basically what precipitates, right? It's sort of a simple approach and it's empirical. And then using those hits to understand the fundamentals of why one mixture would deliver something selective or not. But there's a lot of other ways to do this. I mean, you can use electrochemistry, as other panelists have talked about, to accomplish sustainable metal separations, and a variety of other techniques. You can use light, as we heard about in the last presentations as well. So I think we're in early days. If you're interested, you can, I'll point you to the website again for the center where you can see some specifics. But this is really an open area that's ripe for opportunity through kind of different chemical approaches to develop innovative new solutions and sustainable separations.
Very good. And sticking with you, Dr. Shelter, but also opening this one up really to the other participants, Roger Turner asks, what are the major barriers that you see to rapidly scaling up green chemistry strategies to meet the problems that you've identified? Many of you talked about the potential to go to scale with these new technologies, these new processes, but clearly there are obstacles in the way. What are the major barriers? Invite everyone to take that one on.
That's a very astute question from my friend Roger Turner. Thank you, Roger, for the question. I think, at the moment in terms of metal ion separation, so this is, as I said, a field that's ripe for innovation. And it comes down in some sense to a matter of communication around the question of scale. We need to be in touch from the academic side with folks who are in the mining industry to let them know about this fundamental chemistry that we're developing and the opportunities that exist. I mean, one of the reasons why I chose that gold vignette from the center work is that there's tremendous inertia in this industry and resistance to new chemistry, because people don't really, in the industry, don't really sort of see the value in trying to optimize processes that have worked very well for a long time. It's now that the regulatory climate, though, is changing and giving them pause, because we've had cyanide banned in Europe and other places around the world as a means to do gold extraction. But in general, I think the big barrier is people in the mining industry don't think that there's value to be had, and the around new sustainable solutions, and that the economics have never really worked that well for recycling. So we need fundamental discovery and development of chemistry, and to connect that with folks who are interested in taking it forward in terms of commercialization to develop those opportunities. So communication from industry about what the key needs are, and communication from academics about the opportunities in the new chemistry that's being developed.
And I'll pose the same question to the others on the panel. Again, what are the major barriers that you see to the rapid scaling that all of you described in such glowing and frankly exciting terms?
This is Daryl Mudrow speaking. I'm concerned about the acceptance of these things by the general public, who are now in an anti-science mode. We have so many naysayers out there who are just disbelieving in science for no good reason, I might say, but they're going to play an important part in influencing the regulatory environments in which a lot of these new things are going to be developed will have to play.
I disagree. I think that the major resistance that you see for all of these really exciting, innovative directions is within the industries themselves, because these are using new approaches that people are not familiar with, and their comfort zone does not extend, for example, to mechanochemistry, which was fabulous. What amazing result on ammonia synthesis, but people who do, the chemical engineers don't have that kind of training. And certainly one thing we found with syzygy and with doing light-based reactions is, chemical engineers learn a whole lot, but they don't learn a whole lot of optics. Right? They learn, the oil and gas industry, the Shell, for example, Shell research is filled with petroleum engineers. You can't sort of ask them to think about something outside of their box, because their box is pretty well defined. So it just makes sense that disruptive technologies are going to be on the outside looking in, and they're going to need to have a way to demonstrate themselves relatively independently. It's very hard to find this kind of and I've seen this over and over again. So Daryl, I work in the area also of solar water treatment, because energy is such a huge, huge problem in terms of any kind of water purification. But you see the water treatment people are they're very conventional, very traditional. They say it can't be better than RO. And they're not thinking about, they don't think outside the box. They don't think in terms of innovations. Many people who are more on the science, the chemistry and physics level, they want to think from the ground up, develop a new mechanism. But people who are trained as engineers often, not always, often they think at the systems level. So it's hard for them to think about creating a new technology from the ground up. So you're always that's I think a battle that probably all four of our presentations really represent that inherent intellectual barrier between the established technologies and how to bring in a very different new technology.
Yeah, I think I agree with that. I think that, in many cases, tradition inhibits innovation. And, if it, so in many cases, it's the standpoint of, if it ain't broke, don't fix it. But you have to look at how this plays out in the long run. And even though there are technical and fundamental scientific challenges in many of these technologies that we've presented today, I think that industry has to adopt an approach that enables those types of innovations to at least start to find a foothold in their technologies to see what can work for them. And many companies, I think, are open to that, and they do a bit of their own R&D, but really they're expecting all of that R&D to be done on the academic side and don't want to invest significant dollars necessary to assist in the translation of the technology.
So this for me begs an interesting question, one that I would pose to all of you, and that is it likeliest that the opportunity to exploit the resources needed, the markets needed, the attention needed to exploit the technologies that you've introduced in your talks today, is it likeliest that will come from existing players, established players in these industries, or is it more likely who have the resources, who have the cash, who have access to the credit markets, or is it more likely that it will come via startups and injections of capital into those startups?
I can take that one. So we have seen that the existing players have almost no initiative to try something new until it is well proven. And so the leaps, so existing players will do incremental improvements and they'll do fundamental research that results in good PR, but the true leaps forward, those will be backed by government grant funding, on which existing players will tag on once somebody wins the grant, and venture capital. So the biggest thing that's going to happen in chemistry is more likely to come from Amazon than it is from a big oil and gas company, unfortunately. And it's just because when you look at like one of these operations, for Shell to try something new at one of their refineries, it cost them $10 million to even do the permitting to change their refinery a little bit. And so their like level of burden to try something new is very high, whereas the new players that have a lot of capital from some other industry are more likely to try something crazy. They understand they might fail. They're trying to break in. They know that they have to take risk. The people who are already established, we haven't seen them very willing to take risk. It wasn't until we had more than 20 million in capital. And if you want to know how you accelerate a technology and scale 500,000x over a few years, it's with a whole lot of money. It wasn't until we had that whole lot of money in that we could get the big players to even answer the phone. So.
Speaking of scaling, and I'm Dr. Mudrow, this is a question for you. You referenced toward the end of your talk the opportunities in urban/vertical farming, and unlike some of the other technologies we've seen presented today, this is one that perhaps is easier for the general public to get its head and its arms around. The idea that you can grow things that look like things we're normally used to seeing grow, but grow them in unconventional and yet familiar environments. And I'm wondering, therefore, what your expectation is of how rapidly urban / vertical farming is going to scale as a movement.
Well, I think, first of all, among the adopters from the consumer's point of view, there is already a large body of consumers who are very interested in the freshness of vegetables and who are interested in it being delivered not on trucks from California, but on trucks from the farms that are in your neighborhood. So that body of people are there. The entrepreneurs who are building these companies know this, and they've selected their products on that basis. And I think it's going to grow, probably not through large injections of multi-millions of dollars in capital, but modest amounts of capital to allow these small vendors to build up. They're renting buildings in in declining areas of cities that are buildings that are vacant. We have quite a few vacant buildings in Philadelphia that are owned by the city that are just being not used by anything. They can be acquired for very low cost. The equipment that needs to be put in is not of the same cost of chemical processing plants and so forth. It's beginning to happen.
I'm going to turn to a technical question from another one of our audience members. And this one goes to James, Dr. Bateas. This is from Hata Gebra Michael. And they ask, does the mechanochemistry always have to be a redox reaction?
Well, thank you for that question. I know several of the examples that I gave involved redox chemistry, but there's a lot of work in organic synthesis that doesn't have to go through that particular route. And there are also many examples of not only bond making reactions, but bond breaking reactions from the standpoints of, for example, in polymer extrusion and polymer deformations, you can have mechanophores breaking bonds, and those processes in mechanotransduction are also considered mechanochemistry. And so it really covers a broad scope of chemical processes.
And this is a question, thank you. This is a question that I think I'll address to the whole group because the answer may be different depending on who's answering it. But again, back to the scalability and the potential of some of the technologies that you were referencing. Talked a lot about the size of the opportunity, size of the markets. I wonder if you could talk a little bit about if the technologies you described catch on, where geographically do you see the best opportunity, the first opportunities, perhaps the first and most fertile opportunities for your technologies to go to scale? And a corollary to that would be where ultimately, if not first, perhaps, where ultimately geographically is the biggest opportunity for the technologies that you have elaborated for us today?
So in the case of in the case of the antenna reactor and syzygy technology, we've talked a lot about hydrogen fuel cell vehicles and hydrogen for transportation, and that's something that could be very, that could be implemented in Texas within the city of Houston. We have a joke that because Houston is normally called H-Town, and so we say, look, that syzygy is going to give H-Town a whole new meaning. So so this is a having this become, for example, one could think about one of Trevor's reactors basically being built at every gas station. So you can either have your fossil fuel or you could have your hydrogen vehicle have a fill up at the same types of locations. So it kind of implements that. That's a particular model that would merge really well with the energy transition and would encourage people certainly to be moving towards hydrogen fuel cell vehicles. Certainly trucks are really an almost a no-brainer moving to hydrogen.
Yeah, and I can elaborate more on the geographic nature. We can do a lot of different reactions as a platform, and being able to work with different feedstocks has been a little enlightening. What we see is that any reactions involving methane, or where you need a lot of carbon, so a lot of the hydrocarbon reactions, those are going to be very successful in North America, US and Canada, around the North Sea. What we're seeing is that Asia is looking for zero carbon. And so Asia, I mentioned the ammonia value chain around Asia, whereas ammonia doesn't have as much value as like an energy carrier in North America. We're seeing that in Asia, they are trying to get away from methane and hydrocarbons and are very interested in zero carbon energy carriers, hydrogen, ammonia, et cetera. What we see in Europe is a blend. It depends on where you are in Europe on how they feel about it. It's very differing views if you go to Norway and UK and Switzerland, or if you go further to the east, it's quite mixed. But yeah, the geographic nature depends a lot on the feedstocks that are available and the energy mix that's available. Also, the availability of renewable determines a lot on what kind of chemistry they're interested in there. I think I answered the question by asking more questions, but
That's what the discussion was all about.
Well,
Eric?
David, in the context of critical materials, I mean, this is a really important question of place because critical materials criticality arrives because of sort of supply chain distribution globally. And we've seen, pulling back from that globalized model because of the sort of trade and political implications of critical materials and this kind of interdependence, and some academics call it weaponized interdependence, that has emerged between different nations on the topic. And frankly, sort of the exploitation of the first world against the developing world and the export of waste. So it's interesting. There's, I think, a turning tide on this topic and a growing awareness. The House was having hearings today, the Energy Committee, about critical materials, and it is an issue that spans both sides of the aisle, frankly, for national security reasons as well as energy security reasons. But I think if you're asking sort of where critical materials are going to develop, what the opportunities are, I would say that, I mean, they're everywhere. We have geological scarcity as one aspect of this problem, but rare earths, lithium, and many other essential critical materials are in North America like they are in other places. It's a matter of having sort of regulatory climate and an economic picture that would allow for their development. So, with interest in science and engineering to develop these resources sustainably, that really is the key to bringing this to fruition and having a national supply chain. I mean, there's also discussion around sort of, this infrastructure initiatives right now about trying to develop critical materials that exist in coal byproducts and sort of coal fly ash that have been, exist in piles in different places around the country. So can we extract critical metals from those low-grade sources and also provide jobs to people in those communities that are going to need them as coal becomes less and less favorable as an energy carrier? So, I mean, we just need sort of the will, the regulatory climate, and the right kind of combination of science and technology interest to be able to develop those resources and give good jobs in this emerging sector to people that will need them.
You just made the case.
That's what I do.
So let me just tag on to that. I think, also from the standpoint of good jobs comes also the training that needs to be done for the next generation of scientists working in these industries. I think that's such a critical element. I will say, from the standpoint of mechanochemistry, there's been significantly more buy-in in Europe, looking at this standpoint. I think that is consistent with Europe's currently in a more enhanced vision for sustainability. And so those companies and entities there are working much more closely with scientists on translating mechanochemistry into practice in industry there. I think in the US, there are still many, many, many opportunities. But one thing I was trying to point out, with kind of our eyeing the future concepts are that really, if in situations where you really don't have to use solvent, you have an opportunities for democratizing chemical synthesis globally and using local resources to just do the types of carry out the types of synthesis that you need to do almost in a personalized fashion. And so this is also where many of the folks I've spoken to, for example, from the cost action in Europe, have told me that they've seen greater pickup of this in the pharmaceutical industry. They are quite keen on advancing this opportunity. They have lots of investment in terms of solvent recycling, things like that. And imagine if you can now start to eliminate that cost from your process. That's a huge impact. So I think those are the areas where we might see the biggest impact initially. But as I tried to also say, I would really like to see us do mechanochemistry on the moon.
I'm sure that got everybody's attention. Well, I have a final question, and this question I think is applicable to all of you, and it really is topical. It's of the moment. As we're all well aware, after many, many months of wrangling, we have an infrastructure bill in the United States. It appears that funds will begin to be paid out over the next couple of years. I'm wondering if you could describe what you think. Again, these are early impressions, but if you have any sense of what the implications of that infrastructure package might be for the implementation and the scaling of some of the technologies that you described in your talks. I know there's money in there for water. I know there's money in there for quote unquote energy, but of course the devil's in the details.
Always.
Daryl, sorry, I can't.
So one good aspect of this is the expansion of NSF to be addressing more commercialization. And so many of these really beautiful science and discovery science that could go places gets funded by NSF. So making sure that there's a more meaningful transition that gets you past just, the SBIRs are fine, but they are limited. There are certainly limitations there that SBIRs alone are not going to make things happen. So having more mechanisms that will really help with tech transfer. I mean, I think this is going to be the buzzword for the next 20 years, really, is how we can really go from labs to jobs, basically. And so, so at least what's probably going on in this bill will give a viable start. And also, I think it will breathe a little bit of new life into NSF, because NSF is sort of sometimes perceived by congressmen, depending on whether they're red or blue, whether this is a very useful organization, or they sort of question, is this really sort of staring at your naval science? But showing that this actually will connect discovery to practicality is something that I think will give much more bipartisan buy-in, which I think is going to be good for everyone.
Indeed. Well, on that optimistic note, we will hope that the money that has been allocated or will be allocated will be spent wisely. And I'll offer a further hope that it gets shared out and spent on the kinds of technologies that you all have been describing today. This has been enormously interesting. I want to thank all 5 of our presenters today for sharing their insights in this innovative work in sustainable chemistry. As I mentioned earlier, today's program will be made available shortly to a global audience via YouTube. So please feel free, and we encourage you to share it with your friends, your colleagues globally. We will do the same at the Science History Institute. And as always, we encourage you to follow more of the stories behind the science by engaging with Science History Institute at sciencehistory.org. That concludes our program today, but certainly not the conversation. And I want to thank you very much for joining us today. Thank you all.
Thank you, David. Thank you, everyone.
Thank you.
Thank you.
Thank you so much. Thank you so much.
Enjoyed it.